we can start the session here. So we're very glad to have Dr. Kuma Mishira visiting us as a distinguished lecturer from the Society of Communication. And I think we haven't have her dear coming here visiting us for quite some time. So this is perhaps her first one in a couple of years. And actually Dr. Mishira just arrived in a couple of hours. So, and we're lucky he made it come here. So I think some people may have read his resume on our website. He has a long and distinguished academic record here. So I just briefly talk about some important points here. So Dr. Kuma Mishira obtained his PhD in electrical engineering and MS in mathematics from the University of Iowa in 2015. And he actually got his undergraduate education at the National Institute of Technology in India in 2003. So he's currently a senior fellow at the United States Army Research Laboratory, and he has been working there for 5 years. So Dr. Mishira is a distinguished lecturer of a number of societies of IEEE. He's a dear of the IEEE Communication Society, IEEE Aerospace and Electronic Systems Society, and Computer Technology Society, and IEEE Future Network Society. And he has also very activity in the academic areas. He has been the associate editor of IEEE Transaction Aerospace and Electronic System, where he was awarded Outstanding Editor Recognition in 2021. And he is lead co-authors of several upcoming books on readers. So with that, let's welcome Dr. Mishira. Thank you.
Thank you. Thank you, Richard. And thank you everybody for coming to this talk. And this is my just second time in Minnesota. I was here a couple of weeks ago to attend a conference in Twin Cities. And I'm very excited to visit your chapter and talk about some of the interesting work we have been doing in the areas of reconfigurable intelligent surfaces for various applications where wireless media is involved, like communications and radars. So before I begin, I talked with some of the audience members here, and it appears there are a lot of people with biomedical background or chip design background. May not be familiar with radar, so I'll try to give a more general idea of this topic. And of course, if you're interested in more technical details, we can discuss those as well. Okay, so Richard already mentioned about me, and by the way, in my presentation, I love to put some snippets from my favorite science fiction TV shows and movies, wherever they are talking about radar or communications. So sometimes it is related to the topic I'm going to talk about, otherwise it's just radar and comms and just fun. So just to summarize some of the things that I do, apart from my role in ARL, I'm also a technical advisor of these two very promising startups. First is Hertzwell, that is based in Singapore. It is Asia's first automotive radar startup for self-driving cars. And Aura Intelligent Systems, that is based in Boston, which works on using 5G communications waveform for imaging applications. And my primary interest is in radar, and I explore its connections with signal processing, electromagnetics, communications, and remote sensing. So this particular topic that I'm going to talk about today is at the confluence of several of these areas. It's a very interdisciplinary topic and catching up very fast. I would like to acknowledge a number of my collaborators with whom my collaborative work will be featured in this talk today, from Army Research Lab, Virginia Tech, University of Illinois at Chicago, Luxembourg, IIT Delhi and Rutgers University in New Jersey. And I would like to acknowledge DevCom Army Research Lab and the National Academies of Sciences, Engineering and Medicine for funding this work. So the NASEM is based in Washington, DC, and ARL is in Adelphi, Maryland. Okay, let's look into the motivation of reconfigurable intelligent surfaces. Some of you may have heard about it. It's a term that is becoming very, very popular for past few years. In the electromagnetics community, it has been around for quite some time under the name of metasurfaces. For at least there is a 20 years history of metasurfaces in the electromagnetics and antennas community. But for past 5 to 6 years, the term that Communication Society has been using for that same concept is intelligent surface, and it could be reconfigurable. We'll see in a bit what that means. So that's why RIS has become more popular. But the concept has been around in the electromagnetics community for a very long time. And the motivation for communications engineers to look into RIS is really to enable a number of constraints or features in future wireless networks. So as you can see from some of the references that I've given here, that the future wireless communication systems, they are supposed to support higher data rates, provide very high quality of service, video on demand, gaming, vehicular communications, and so on, should have low power consumption. So these are all the constraints or features that 5G, 6G, these kind of systems are supposed to have. And there has been a lot of work on how we can support these features, both on the hardware aspect as well as on the signal processing, and including communications protocol as well. So on the hardware aspect, people want to experiment with those kind of antennas or transmit receive systems which have a smaller form factor. And this is where reconfigurable intelligent surface or metasurfaces, they come into play, because they can provide very small form factor, and we'll see how that happens. Moreover, a lot of these surfaces, because there is a word reconfigurable in that, you can think of it as a programmable surface, where we can use that surface. And whenever I'm saying surface, that is also a kind of antenna. So it's a reconfigurable antenna or programmable antenna. And the goal is to actually achieve many different types of beam patterns that normally are difficult to do so using a standard phased array antenna. So that's where metasurfaces, they come into picture. Here is a comparison of the metasurface antennas with two very common antennas that are used for a variety of application in astronomy or radar or wireless communications and so on. So some of you may be familiar with phased arrays, also used in ultrasound, for example, or acoustics. An array of microphones is also a phased array. So when we use a number of antennas together, it forms an array, and that can give us a much higher angular resolution, as well as you don't have to mechanically scan the antenna, because you can do that electronically using a phased array. So that's what phased arrays are used for. They are very expensive, although very popular as well, both in military as well as in wireless communications industry. And compared to the reflector dish, which actually scans mechanically, phased arrays do not have that mechanical movement. So reflector dishes, they have a moderate cost, but then they can only have a single beam pattern. We cannot tweak that beam pattern. In phased array, by tweaking the phases or the inputs to each one of the individual antennas, you can shape the beam pattern. We cannot do that with reflector dishes. So because of all these characteristics, phased arrays have become very popular for past many decades over reflector dishes, except that they are a little bit more expensive, and they have this very highly complex circuitry which is designed to control this beam pattern. So reflector dishes, there is no such complex circuitry, because there's only one beam pattern there, right? Then we come to metasurface antennas. So in a very simple language, if I have to explain metasurface antennas, it does everything that a phased array does, except that it has a very small form factor. So small form factor, low cost, low power consumption, and we'll see why that happens in a bit. So it has all these interesting properties. It has some control circuitry, not as complex as phased arrays, but very minimal control circuitry. So for all those applications where size, area, weight, power consumption, these constraints are critical, for example, small satellites or self-driving cars or UAVs, drones, where we have constraint on what kind of hardware we can put on these kind of systems, because area is not like a big military radar and so on. Every inch on a self-driving car counts because there are so many sensors that need to be fit on those vehicles. Same with small satellites. We want antennas to be very compact on those kind of applications. So for these kind of applications, metasurfaces, so MTS is for metasurface here in this blue box, and RMTS is the reconfigurable metasurface. That is actually a low-cost, small form factor alternative to phased arrays. That's why they have become very popular. Now, how this low cost, lightweight, all these features, they come into play in metasurface? For that, we only have to look into how the conventional wireless radar or communications transmitter or receiver looks like. So the first figure that you see here on top right is the conventional wireless transceiver, where you have an antenna array, and at the back end of the antenna array, there is a lot of analog circuitry. We have power amplifier, filters, mixers, and if it was a receiver, you'll have limiters, low noise amplifiers, and so on. And then we have the digital module. What metasurface or this reconfigurable intelligent surface does is to actually combine or integrate the analog part into the antenna aperture. So this is what we see here at the bottom right, that we have an antenna which is programmable, which can perform some of those analog functions. So we have a programmable metasurface with some circuitry, control circuitry that I had alluded to in the slide before this. And then you have a digital or baseband module, which was there in the conventional case as well. So because of this, if we are able to eliminate a number of analog components, then it is very useful, because it can really bring down the cost and power consumption, and the area could also be lower. So that's why metasurfaces, people are looking into this more and more in the communications industry as well as in the remote sensing industry. So there has been a lot of prior works. As I said, the antennas or electromagnetics community has been working on this for a while. They have been examining it from the electromagnetics perspective and from the materials perspective. For example, which materials could be appropriate to design this kind of programmable metasurface. And I'll give some examples in a bit why and how this materials part becomes important. But then applications of metasurfaces for wireless communications, that is very, very recent. Just like I said, last 5 years. And nowadays, almost every day I see some papers being published in communications publications, our Comstock Society transactions. So it has become very popular. What we have been doing in Army Research Lab is to actually combine the conclusions that have been obtained by both communications community as well as electromagnetics community. For example, we want to examine some new types of modulations with metasurfaces that have not been implemented before by other researchers. We also want to make these designs electromagnetically compatible. Normally, in the standard reconfigurable intelligent surface research in the communications community, they do not take into account electromagnetic models. It is more like a theoretical mathematical model, and then people carry out the analysis. But then we don't know if those designs are really implementable or not, and that's why we want to look into the electromagnetically compliant design. And I'll show how we actually bring the two things together. Here is a summary of what a programmable configurable intelligent surface can do. Such a surface actually consists of these unit elements or its constituent units, which we call as meta atoms. Meta-atoms are placed at sub-wavelength apart. So normally in a phased array, one antenna is typically the inter-element spacing with respect to another antenna is half wavelength, lambda over 2. But here we use a lot of meta-atoms in a surface, and they are placed at a spacing much lower than lambda over 2, so sub-wavelength spacing. And by controlling through a digital module the property of each one of those meta-atoms, the overall beam pattern or overall response of the surface is controlled. So essentially, these meta-atoms, and they could be either the same type of meta-atoms, or they could even be diverse, different types, different shapes, and so on. Depends on your application and how much control you want of the surface, because control of the surface is not just using one signal for the whole surface. It is by combining the signal to each one of the meta-atoms. So that gives more control, and as a result of this, as you can see from some applications related to beam forming on the left side, we have beam steering that could be achieved just by digitally controlling such a surface. You can get multiple beams, or you can get an adaptive beam pattern. All of this could be done if we can change the phase or some other property of the meta-atom, individually each meta-atom. Similarly, modulation, using the same surface, we can achieve different types of modulation just by programming it. Usually, when we have such an antenna in wireless communications, it is tailored for just one type of modulation. But here, you can have the same surface, and because there is no analog circuitry, different analog circuitry involved here, it is combined with this programmable surface. You don't have to change the hardware of the analog circuitry to go from one type of modulation to another modulation, because all of that part is digital now, control is digital. So the same surface could be used for various types of modulation, some of the conventional ones like frequency or phase modulation, as well as some new types of modulation like polarization modulation. So this programmability is actually very useful and very powerful for these future wireless networks. And just to go over the terminology that has been used across electromagnetics and communication. So I already mentioned that electromagnetics community uses the term meta-surface, which is a 2D version of what we call as metamaterials. Metamaterials are synthetic materials with properties that are usually not found in nature. So they are synthesized in the lab, and they have very unusual properties, hence this name has come up, metamaterials. So a few years ago, almost I think around 2008, 2009, some of you might have read this news item that Harry Potter's invisibility cloak has been designed by scientists. And that was when the metamaterials papers were first published. So, well, there was no cloak. It was a very limited demonstration of invisibility at a certain frequency for a specific type of material, and then a bunch of other constraints. That's what they meant, that you can use metamaterials for those kind of applications. Now, those materials are not found naturally. They need to be synthesized in the lab. So that's why we call them metamaterials. And it is typically 3D, but when we use it in 2D, then we call it meta-surface. There are other terms like meta-grating, hydrogen surface, meta-film. These are just different types of implementations of meta-surfaces. Then in the communications community, when people started using this, at the fusion of communications and electromagnetics, then other terms came up that, okay, meta-surface, if we want to change its properties on the fly, we call it reconfigurable meta-surface, and it has other names like coding meta-surface, programmable, and so on. And then in the communications community, initially LIS became more popular, large intelligent surface, and later on people started using reconfigurable intelligent surface, which has now become a standard. Within this RIS, there is a specific subset of these surfaces, which are IRS. It's not the agency you deal with in April, it's intelligent reflecting surface. So intelligent reflecting surface is a type of RIS, but it only acts as a reflector, as a passive surface. So it is typically not used at a transmitter or receiver, but rather as part of the wireless channel to manipulate the channel. And this is what we call as smart radio environment, where transmitter receiver are the traditional transmitter, as you can see from this graphic at the bottom right. But the wireless environment has these IRS installed, which can manipulate the wireless media. For example, instead of doing line of sight communications, using IRS, you can also do non-line of sight communications or non-line of sight sensing. So this is why we call deployment of these IRSs on infrastructure, that's how it has been envisaged as a smart radio environment. There has also been some implementations by industry. NTT Docomo has consistently demonstrated every year since 2021 open air transmission using reconfigurable intelligent surface aided transmitters. In MIT, Hari Balakrishnan's lab has produced what we call as smart walls, which is a number of these IRSs deployed on a wall, and then it has been shown that it can act as a reflector. You can do non-line of sight sensing and comms. So there have been now practical implementations as well. Okay. Now with that background, let's look into some of the details and some of the work that we have been doing. I'll just give some examples where we are using metasurfaces for wireless comms and what is new there, what are the challenges. Then for sensing, and I'll use the word sensing interchangeably with radar, so metasurfaces for sensing or radar. And then we also have some work on metasurfaces for joint radar communications, and we'll see why that is necessary or interesting. And I'll end this talk with some work that we have been doing using machine learning. So in any one of these talks, without machine learning, the talk doesn't end these days. There's always a machine learning component. But what we are doing is different. I'm sure everyone would say that what we are doing is different. But here, we are using machine learning to actually design the metasurface. And that is a very nice application to see how it works. Okay, so conventionally, how the metasurface is controlled. So as I mentioned earlier, metasurface comprises of these constituent units, which we call as meta-atoms. And each meta-atom, by controlling it, we can control the response of the whole surface. Conventional meta-atoms, they are designed on a substrate. You put some shapes of a metal, which is what you see here, which is called passive meta-atom. But however, once you fabricate this, you cannot change its response, because the way it works is that its dimensions, whatever shape you have taken, rectangle or circle, or we'll see some other shapes as well, those dimensions, they determine its surface impedance or some other electromagnetic property. And that surface impedance determines its phase response. And by combining the phase response of all the meta-atoms, we get the phase response of the metasurface. Because this response is connected to the dimension, once you have fabricated this, it cannot be changed. So this is what the conventional meta-atoms were about. But then what the work that we started in ARL is that could we have a mechanism where we can change the response on the fly? That's what we call as active meta-atoms or the reconfigurable or programmable surface. And how do we do that? So we use, for example, here I'm showing active meta-atom from one of our papers, which is based on these Varactor diodes. And we have a digital control module that I had shown earlier. That is the control circuitry for the metasurface. Through that, we change the bias voltage of each one of these active meta-atom elements. That changes its capacitance, which then changes its surface impedance, and then we finally obtain the phase response. So on the fly, because here it is not, the response is not directly related to the dimensions of the meta-atom, but rather you can change the surface impedance by changing the bias voltage signal. So this is what makes it programmable, and this research has become very popular now that, okay, we want to do active tuning because passive tuning has several limitations. So this gives an example of how this change is done. And then here I'm showing one of the implementations that we did, and shown here is actually a full wave solver, which is an electromagnetic software, where we show that, okay, if you can change the signal to this digital control module and tune each one of the meta items, you can actually obtain a beam like this, which is a composite signal of phase response of all the meta items. And through this, once we have this, then we wanted to experiment with some more complicated wireless communication signaling. For example, we want to look into what we call as index modulation, and that is what the next module I'm going to talk about. So just to summarize this module, the goal is to achieve a better control of the meta surface, which is in turn is achieved by controlling each one of the meta items. Conventional design of meta items is based on physical dimensions, which once fabricated cannot be changed. So we resort to active meta item design, where there's an active element like a vector diode, and you change its bias voltage and then control the overall response of the meta surface. And the overall response manifests itself in terms of this radiation patterns like these. And we can manipulate this radiation pattern by changing the digital control signaling. Okay. So, as I said, people have been working on meta surfaces and communication communities for past few years, but there were some certain applications that they had not looked into, and we wanted to examine index modulation. I mean, there were some other modulations that people had examined with meta surfaces, but we want to generalize it, and that is the index modulation. So what is index modulation? Pretty much every modulation could be called index modulation. For example, orthogonal frequency division multiplexing is an index modulation. So in a very generic terms, index modulation is a modulation technique where we use some kind of wireless media resources as an index to modulate the bits. So when we are using OFDM, then the subcarriers, the frequency subcarriers, they are the indices that we are modulating the bits on. In case of spatial modulation, number of antennas. So antennas are used to modulate the bits, as you can see in figure A here. And then when we are doing space-time modulation, then we are using both resources, the time slots as well as the number of antennas, to modulate the bits. So obviously all kinds of modulation, if you are using pulse width modulation, then we are using the width as a resource and so on, right? So it's a very generic term. Specifically, spatial modulation, that is using the number of antennas to modulate the bits, that has been suggested at least 2-3 decades back. But it did not become very popular, because if we want to use number of antennas to modulate the bits, you actually need to have a lot of antennas. I mean, in OFDM, we have more than 1,000 subcarriers to modulate the signal. Now, to have 1,000 antennas to do the same thing, that would cost a lot. You will have to have a lot of antennas, then it's back-end circuitry and so on. But with the advent of meta surfaces, which is bringing down the cost, and you can have a lot of these antenna elements, and you can combine the analog circuitry or reduce it by integrating it with the aperture, spatial modulation is now back in business, so to say. And in particular, people now think that with meta surfaces, we can actually implement it in a more cost-effective manner. So that's why index modulation, specifically spatial modulation, was the starting point of research in communications community to examine meta surfaces. Of course, it has now been expanded to a lot of other wireless media resources as well. For example, polarization, we'll see an example of that. Shown here is an example of index modulation implemented through these surfaces across various different wireless media resources. This is from one of our papers that has been accepted in IEEE Journal of Selected Topics on Signal Processing. So we show here that the same surface could be used to achieve classical spatial modulation, space shift keying, generalized spatial modulation, OFDM, as well as media-based modulation. So just like spatial modulation was suggested about 25 years ago, but it didn't become very popular because there weren't any means to actually implement it. Similarly, media-based modulation, where the channel itself is used as a index to modulate the bits, that was suggested about 10 years ago. But again, there wasn't a technique to implement this. Now we have a way with metasurfaces to actually control the channel and to achieve these dynamic beam patterns, a very powerful beam controlling technology. Now media-based modulation is being investigated once again for its potential application in future wireless communications. So a number of these index modulations could be achieved with metasurfaces. That is very promising for 6G, for example. Here's the meta-atom design that we had in the surfaces that I just showed you. So we had this time-varying meta-atom design using varictor diodes, and shown here is that, okay, we have one atom, and then how it scales up, how we actually stack it together to create a bigger surface. And what you see in the bottom panel is the full wave electromagnetic simulation in HFSS, the electromagnetic software. We are just by controlling the digital part of the signal, we show that the beam that you get in this figure A in the bottom panel, that could be steered in any direction as we show in this subfigure B here in the bottom panel. And this is a 20 by 20 metasurfaces, so that is a 20 by 20 array of meta-atoms. So this is very powerful. There's no backend circuitry or minimal backend circuitry, and just through an FPGA control module, we are able to change the beam pattern. Here is another set of results that we had that we published in IEEE 99 wireless propagation letters, where we are trying to implement OFDM index modulation using metasurfaces, the same metasurface that I just showed. And then this is a very good example of bringing communications and electromagnetics together. Normally, people have a theoretical or a mathematical model, and then they just simulate it to see what kind of bit error rates they get or what kind of spectral efficiency they get with that kind of modulation. But here we actually integrate this full wave solver model that I showed in the previous slide in the simulation software, and then we see that if such a signal is transmitted and decoded at the receiver, what kind of performance characteristics we can get. So the bit error rate curves that you see here are really after including the electromagnetics of such a surface. It is not completely theoretical. Okay, so now we know that, okay, we can implement index modulation and we can save all these resources. There's not much analog circuitry. What are other interesting things we could do with metasurfaces? So then we scale up and we start looking at other wireless media resources. So one of them is polarization. Can we use polarization itself? So we can generate many different types of polarization. I mean, horizontal and vertical are very popular, but you can have a full array of polarization, 8 or 16 different types. And if we can have that, then can we use it for modulating this wireless communication signal? So I'm showing here another graphic of this index modulation. So we already know the spatial modulation case, and when we use both polarization and space, that is 4 polarizations, for example, in figure D, and by space I mean number of antennas. So we use together different number of antennas, different number of polarization. That gives us more flexibility to embed additional bits or additional information in the signal that we are transmitting, because now we have 2 different resources to control. As with spatial modulation before, polarization modulation was also suggested in the literature, but we did not have either the transmitters or even different types of materials available which could very quickly switch between different polarizations. So it was not practical to implement this. Even in metasurfaces, spatial I have already shown, but then polarization is difficult to implement as a modulation technique, because not all materials are actually able to switch between different polarizations. There's a lot of research. As I said, the electromagnetics community does a lot of research on the materials aspect, which could be good for implementation. And polarization is one such aspect where we did not have a lot of research before. In ARL, we looked into barium, strontium, titanate substrate, and this is a slide from one of my colleagues' papers, where they showed that if you use BST, that is a material that can switch between at least 16 different polarizations. So we can have 16 polarization states and then combine it with several number of antennas, and that gives us a lot more resources to embed the information bits. So the same is shown here. We are using, let's say, the 2 bits. So that is, those are the horizontal rows that you see. So first 2 bits, we use it to select the sub-aperture of the surface. So we divide the whole surface into 4 sub-apertures, and we select any 2 of them using the first 2 bits. And the rest of the bits that are, there are about 10 bits, that we use to select a type of a polarization. Theoretically, this was suggested around 2019 or 2018, but there weren't any implementations because of this material research aspect that I mentioned. But our work has actually shown that a BST meta-atom can actually achieve this. And then here are some other curves where we are showing that as you increase the number of polarizations, you can actually obtain a better bit error rate performance. And again, while producing these curves, we don't just have an equation and then we start plotting them. We integrate it with the electromagnetic models of this BST, and then we show what kind of bit error rates could be obtained. Okay, so this was just a snippet of applications that metasurfaces could be useful for wireless communications. Now we come to sensing. Here we are doing largely theoretical work in signal processing. That means equations, theorems, this kind of analysis. I'll just give a kind of a quick overview here, considering the background of everyone. But if you're more interested, we can go into more details here. But my goal here is to show what kind of problems show up when we want to use metasurfaces for sensing or joint sensing comms application, so that it gives you an idea of the interesting problems that lie in this area. And if you're interested, what kind of references you can look into for more information. So the application is as follows, the primary application. Usually in a radar, we have a transmitter. It sends out an electromagnetic wave towards a target of interest, could be an aircraft, a human intruder, or any such object of interest. And when this electromagnetic wave interacts with this target of interest, its properties change. So as we know, electromagnetic wave is characterized by its frequency, amplitude, and polarization state. When there is an interaction of electromagnetic wave with the target, all these 3 properties change. When the wave is reflected back and is captured or intercepted by the receiver of the radar, then by monitoring the changes in these properties, that is amplitude, frequency, and polarization state, we can get a lot of information about the target. For example, the amplitude, if it decreases, then this attenuation in the amplitude can tell us about the size or shape of the target. If there is a change in the frequency, that can tell us about the Doppler velocity of the target, which is what cops use to determine if you're speeding or not. They are just observing the change in the frequency, and the change in frequency is directly proportional to the Doppler velocity of the target. Depending on how delayed the signal comes back after it has been transmitted and then it comes back to the receiver, that delay tells us about the range of the target with respect to the receiver. The further the target, the signal will come back later. If it is closer, you will get the signal back quickly. By monitoring this delay, we can get the exact location of the target. And by monitoring the polarization state, many other characteristics could also be found. Obviously, all of this is in line of sight. But if there is an obstruction in between, we cannot sense the target. That's where metasurfaces in particular in the form of IRS, intelligent reflecting surface, comes into picture. So we deploy IRSs on buildings or other infrastructure, and when the radar is unable to directly see the target, it transmits a signal towards the IRS, and because IRS is a controllable, programmable unit, it can steer that signal towards the target. So the line of sight is between the IRS and target, but not between target and radar. But by deploying these IRSs, we can do non-line of sight sensing. Same could also be achieved for non-line of sight communications. So this is the work that I've been doing with my colleagues in University of Illinois at Chicago. And we have done a lot of work on analyzing this received signal, what are its mathematical models, and so on. So I'll just give a very quick overview of what kind of problems they show up here. Okay, so here, whenever we are doing this kind of analysis, we have a transmit signal. So the very first equation that you see, SOFDM, that is our transmit signal. Then the transmit signal interacts with the target. And the way we model the target is this HLM, which is the non-line of sight channel. It has all the unknowns of the target, like Doppler velocity, its distance, its angular location, and so on. And when we get a received signal, then after some tedious algebra, we get this last equation, equation 3, where Y is the received signal, discrete received signal. The matrix A has information about the transmit signal itself. X has all these other unknowns about the target, for example, its Doppler velocity or delay and so on. And then PV, that is the characteristics of the IRS. So IRS, the way we model it is that you have these different meta atoms. We model it as a matrix, and each one of the unit or element of that matrix is a phase of one of the meta atoms. So if I have 100 meta atoms, I have this matrix with 100 elements. Each element is a phase. The goal here is that if I want to extract X from Y, I must have a good A, that is a good waveform that I transmitted, and I must have a good PV. So N is the noise, by the way. PV is how these matrices should look like, and if you have multiple IRSs, you have to design these multiple matrices. So typical signal processing problems in this kind of application is that to extract X, I must have a good A and P. What are those good A and P? In order to find those good A and P, typically you have to solve optimization problems like the one that is shown here with certain constraints. And these optimization problems are actually very difficult to solve. They are non-convex, and people who are familiar with optimization theory would recall that if the problem is non-convex, we have to actually relax it in such a way that it becomes more tractable. We have to make it convex. And convex problems are tractable. We have algorithms to solve convex problems. So in IRS-aided radar, problem is of waveform design, that was A, matrix A, and to design the beamformer for the IRS, that was that PV matrix or any matrix related to IRS. All these problems are non-convex. In order to convexify them, we resort to many different signal processing tools that are provided in one of those papers. So these are the typical problems that we see in IRS-aided radar problems. Now we expand it a little bit. So shown here is that, okay, if you use just one IRS, then the detection performance, although better than not having the line of sight at all, it is still very weak. So you must use multiple IRSs so that at least if you are unable to see the target through one IRS, you can see it with other IRSs, and overall you can detect the target. So use of multiple IRSs was also something that we suggested first in the literature, but that is also a complex problem to solve, because then there could be interference from one IRS to another IRS. And again, this constraint needs to be input to this optimization, this complex optimization problem, which makes it even more difficult to solve. So a lot of interesting results in this area. They are in form of these theoretical algorithms on how to address these specific or special constraints. Okay. Now that we have seen metasurface applications for comms, metasurface applications for sensing, what happens when we want to join both radar and communications? And why would that be the case? That is because of the constraint in spectral crowding. So with the advent of new radar applications, new wireless communications applications, all these applications, they require wider bandwidth. But spectrum, RF spectrum is a scarce natural resource. We do not have infinite bandwidth to allocate to all of these service providers or emitters. So the way forward, and this is a very popular topic and is my another area of research, is can we share the spectrum between different communications applications and different radar applications? This is what is called joint radar communications. So in this context, we have been doing a lot of work, but if you want to add IRS into this problem, that is a transmitter which can double up as both radar and communications, and it wants to do non-line of sight sensing, non-line of sight communications, then add IRS into the mix. And this is what we have done in our recent work. So the very first one that you are seeing is just the IRS aided communication system. We have this base station, that tower that you see, and it does not have a direct path to the communications users, so it is communicating through the IRS, which has been deployed on infrastructure. Same thing could be done with a radar system. And here in the last one, we are combining. So now we have dual function base station, or DFBS, which acts as both this one-way communication system and the two-way radar system. It's a common waveform, common hardware. But its path to both the target and communications users is blocked. So the way it is going to sense its target and communicate with users is by deploying many IRSs. So you have already seen that the problem is very complex when we want to do IRS-aided radar. We have these matrices that we have to design, we have to do the waveform design and so on. Now when we are trying to combine both of them, it's actually even more complex. And just to show you very briefly how complex it could be, I'll just show some of the equations, not to scare anyone, but just to show you how many unknowns are there in these kind of problems. So now we have all these unknown radar channels, right? That is the information about the target. We have communications channels, and we have this bunch of matrices that we have to either decipher or we have to design. And then the final equation that we get, for example, the communications equation that you see there, it is a lot of unknowns that you need to design. And you can easily see that the problem is actually extremely difficult to solve. It manifests itself finally after a lot of complex algebra. There are like quite a few pages we spend in deriving the final form, and then we get this final optimization problem that is shown here. Its objective function is a weighted signal to noise ratio, that is SINR for radar and SINR for communications, subjected to a bunch of constraints. And we have to find, like I said, waveform for radar, beamformer or precoder for communications, and all these matrices for multiple IRS. It's also non-convex problem, and by now you would have understood that whenever I say non-convex, that means it's just don't even touch it, because if you cannot convexify it, it will be very difficult to solve. So when we get this non-convex problem, there are many techniques to actually address it. For example, you fix one of the variables, and then it turns out if one variable is constant, the problem becomes more tractable. So you solve that sub-problem. In the next step, you make the other variable constant, and you solve the problem for this another variable, and then iterate between them until convergence. That is also one of the way in which this problem is addressed. Okay, then I come to the final segment of this talk, which is actually very interesting. So I wanted to spend a few minutes on this, which is using machine learning for designing metasurfaces. And when I say designing metasurfaces, it's designing meta-atoms, because you design one meta-atom, just repeat it, you get a surface. So why it is interesting? Typically, when we want to design these surfaces, we have to select a shape of a meta-atom. So you already saw that rectangular shape in the very first slide. In the literature, there are a bunch of other shapes that have come up, and here is a montage of different shapes like a coffee bean shape, anchor shape, and so on. These are the standard shapes that are used for meta-atoms. But then which shape to use for to get a desired spectral response, that is a very time-consuming and tedious task. You start with one shape, you solve Maxwell's equations, and then you see what response you get. If that is not a desired response, you iterate. Then you again change the dimensions. If you had a bigger rectangle, now you take a smaller rectangle. You keep on iterating like this. So it's a very iterative and time-consuming procedure. Usually it takes months or weeks for sure to arrive at a good shape for your application. We wanted to actually automate this process. And this is where we wanted to use machine learning. So here I show some more details on how this is done. As I mentioned earlier, you have a physical dimension that controls some electromagnetic property. So if you see this diagram here, the physical metasurface has all those shapes that I'm showing there. So I'm talking about this panel just below this label diagram. So below physical shape, I show some of the shapes that we use. All those shapes have different electromagnetic properties, and then those properties determine what response it will have. In order to arrive at any one of the shapes, you should just solve these Maxwell equations for each one of the shapes, each one of the dimensions. It's a very exhaustive process, right? And then you find out what should be a good shape. So we want to do the inverse design. If I have a spectral response, can I input it to a deep learning network, and then it can tell me, okay, this is the shape you should use, right? So forward, some people have done the forward prediction that is very common in literature, that they don't want to solve these Maxwell's equations. So they have a shape, they input it to the network, and then they want to see what is the spectral response. But again, they will have to iterate again, right? If they don't get a desired response, they'll again have to change the shape. Why not just input the spectral response to the network and then get the shape? That is the question that we wanted to pursue. During the COVID times, you might have seen this one press release from MIT, which talked about, can we design a protein combination for the vaccine using deep learning? So we know the response we want to the virus. Can we feed it to a deep learning network? And the deep learning network tells us this is the protein structure that you should use. And I'm not sure if they actually experimented with it, but they did show that they could get a protein structure which resembles very closely to the actual vaccine's protein structure. That was an example of inverse design. This is very similar. So the next question that arises is, which is a good deep learning network to use? And we used GAN, the generative adversarial network. Instead of using just one deep learning network, GAN uses a combination of deep learning network. It has two deep learning networks. One is called generator, another one is called discriminator. Generator produces fake outputs, and the discriminator, based on its training, then distinguishes that this is a fake output or a fake shape and this is the real shape. And they have a kind of a game theoretic relationship with each other, which makes the performance of the overall network way more robust and accurate compared to using just one deep learning network. So having selected the network, next part is to train the network. And how to train the network? There was some work by Stanford nanophotonics group. They were doing a similar work, but in nanophotonics, not with metasurfaces, where they used handwritten digits, the shape of handwritten digits to train the network. And then that was a trained network they wanted to use to find out the shapes of their nanophotonic structure. But then that's not what we want to do, because the actual metasurface or meta-atom structures, they are not handwritten digits. They are shapes like these. So we took about 12 of these shapes from the existing literature, and we generated a large training data set by varying its dimensions as shown here. And we trained our network using this training set. This is more realistic than using cat and dog images to train the network, because that is not our application, or even using handwritten digits. So shown here is one example that I have that meta-atom shape which looks like this anchor, and then I try to get its spectral response at different polarizations, both magnitude and phase. This is what I get by using an HFSS electromagnetic software. Now the goal is to use these shapes that we got, these responses that we got from the actual simulation software as input to the network, and then see what it gives us. So here is an example. So we took all these responses that you see in the first two columns of each row, and those are the inputs to the network. And then during training, we see what kind of shape we are getting. Once we get the shape, which is the second last column in each one of these rows, we compare its performance, that okay, this is the shape we got with different dimensions. We then input it to the electromagnetic software and then see what response it gives. And then we compare that output response, the verified actual response, with our input. It turns out it's very close. Okay, so this sounds very interesting, but and may also be simplistic, that okay, you're inputting these responses, and you have trained your network with about 12 shapes, so obviously you are going to get one of those 12 classes. This is where GAN is very useful, because GAN can not only produce the class for which you trained GAN with, but can also help you discover new classes. So the last two rows that you see here, the row M and N, those are the shapes that we never trained GAN with, but it is helping us discover new classes or new shapes that all these 12 shapes are not the ones that are good for your given spectral response. Rather, I've discovered these other shapes like S shape or that other shape that you see there, and this could be better. This opens up a lot of interesting research opportunities, because we do not have an electromagnetic study for these new shapes. All other shapes, they had some electromagnetic background, but not these new shapes. So discovery of new shapes, new classes, in case of COVID vaccine example, discovery of new protein patterns that scientists had no clue about, that can be enabled with the use of GAN. And then we have shown that just to obtain greater control of the meta surface, so far there was just one shape, but then typically that still will not give you a better control. We need to have every meta atom with multiple layers. Multiple shapes for each layer could be obtained, and we use a slightly different, more complex GAN to achieve this. So here we are representing 3-layer meta atom with 3 different colors, and then we show that okay, what were the training images, what are the generated images, and even in the generated images there are cases where we are getting some new shapes, like those blobs, green blobs that you see. We never trained the network with those. Okay, so in summary, meta surfaces, they are low-cost antennas in which analog circuitry is integrated. When you use it as part of transceiver, transmitter or receiver, it helps in making small form factor wireless receivers or transmitters. When you use it as part of the channel, it can help you in manipulating certain characteristics of the channel to enable applications such as non-line of sight wireless communications or non-line of sight sensing or imaging. And then to design the meta surfaces, there are a lot of deep learning applications that are coming out. Recently, we contributed a chapter. There's a book by Doug Werner from Penn State, published by Wiley IEEE Press, which is AI-empowered electromagnetics. And there you will find a lot of applications on the use of machine learning for meta surface applications. And I also want to plug in my upcoming book to be published by Wiley IEEE Press. So I mentioned this joint radar communications very briefly in one of the segments. It's a very active topic, and typically I do another distinguished lecture just on that topic with more details, but you can find a lot of interesting chapters in this book. So with that, I would like to thank all of you for coming to the talk, and I'm happy to take any questions you guys might have.
Thank you very much, Dr. Bashir. That's a very interesting talk. There are a lot of things, especially the answers again, network and generate something not retrained. That's kind of a deep fake.
Exactly. Yeah.
So with that, any questions from the audience? Yes. Yeah.
So with regard to, you mentioned like the small shapes that get used are then multiplied or just replicated over a large sheet. Do you have to use the same shape over the entire sheet, or can you mix and match shapes to get different effects?
You need to mix and match, but then there are other issues that may arise. So each one of these shapes has certain electromagnetic properties. And the first question is, how do people even come up with these standard shapes? Not the ones that GAN is discovering, but like coffee bean shape and all of them. And there is a very nice theory at the background of how those shapes are obtained. Some have bi-anisotropic properties, some have better tensor permittivity, and so on. Now, if you actually do mix and match, overall performance with respect to the bi-anisotropic properties, that will decrease because you use just one such shape which had a good property like that. Another shape could be better for polarization, but since you have used it just once because it's a very heterogeneous thing that you have made up, you may not get good enough properties that shape, if it is the same shape is repeated across the surface, will give. You will get some kind of surface, it will do something, but then it may not have the best of all of them, right? Because you just had one such shape in your whole meta surface.
Mm-hmm.
So we're kind of for those that are asked me, maybe just one or two questions.
So a lot of what you talked about is optimizing for a very busy, limited resource called bandwidth or spectrum to work with. In biomedical applications, let's say, that's maybe not quite as a big of a concern, right? There's a lot of, you're working in a controlled environment, that's not much effort. How could this be leveraged? What are the other things you could optimize for to make these metasurfaces or the antennas useful in biomedical applications?
That's a very good question. So for this, I go back to some of the introductory material that I have shown. So essentially, what is metasurface replacing in the existing systems? It is replacing a phased array. Wherever you have a phased array, that's where metasurface could be useful. So of course, wireless communication, sonar, radar, they all use phased array antennas. In biomedical, then we have to think about, is there an application where an array is used? Answer is yes, ultrasound. Ultrasound is one such case where we have an array of sensors. And if you want a low form factor, low cost ultrasound sensor, in that case, metasurfaces can replace the sensor and its backend circuitry. So metasurface does not do anything that phased array cannot do, which is what I said in the beginning. It does all those things that phased array does, but with less cost, low power consumption, low form factor.
So to the issue of ultrasound works because of the piezoelectric effect. It's a mechanical effect, not a strictly electronic effect. Are metamaterials, as you look at them, do they apply to mechanical transduction?
There are some works on it. I'm not an expert in that area, but yes, there are some works on using this for acoustic applications, using it for, like what you're saying, some mechanical related applications. But I'm not an expert in that. But the essential takeaway here is that wherever you have a sensor array, that's where metasurface can fit in. So ultrasound is one such case, and that's why this could be useful there. Details are available in the literature, but I'm not an expert on that topic.
Very good, thanks so much.
Any other questions from the audience? Okay, maybe a thanks to Dr. Mashera.
Thank you.
And also, we're going to have for dinner with our speaker at 8:30. If anyone would like to join us, welcome. We'll have dinner at